Hello students, in previous lecture I have defined equivalent matrix and we have taken the sufficient condition for equivalent matrix which is not necessary condition. What is that sufficient condition? Two matrix D1, D2 for matrix for non-empty set X are equivalent if there exists positive numbers K1, K2 greater than 0 such that K1 times D1 of X file is equal, D2 of X file is equal D1 of XY for any XY belonging to X. We'll use this sufficient condition to show that matrix are equivalent on given non-empty set in this lecture. Okay, so take our first example. Example 1. Matrix D1, D2, D infinity for Rn is equal to set of x bar is equal to x1 up to x2 dot dot up to xn, x size belongs to R, n greater equal to are defined as what is D1 of x bar y bar summation of I equal to 1 to n mod of xi minus yi. This is known as taxi cab matrix. Okay, D2 of x bar y bar is equal to summation of xi minus yi bracket square I equal to 1 to n whole thing raised to half, and d infinity of x bar y bar is defined as maximum of mod of xi minus yi 1 less equal I less equal n. So that any two matrix among D1, D2, D infinity are equivalent. Okay, so solution. So first, to show D1, D2 are equivalent. Matrix on Rn. So for this, if I take D2 of x bar y bar its square, I'll get it is summation of xi minus yi its bracket square I equal to 1 to n, and this is less equal summation of mod of xi minus yi I equal to 1 to n bracket square. Is it clear? Here this is nothing but x1 minus y1 square plus x2 minus y2 square plus dot dot up to xn minus yn square, sum of n terms. And for this, mod of xi minus y is nothing but xi minus y bracket square. So mod x1 minus y1 plus mod x2 minus y2 plus dot dot up to mod xn minus ym bracket square is nothing but sum of n squares first. x1 minus y1 bracket square plus x2 minus y2 bracket square plus dot dot up to xn minus ym bracket square plus 2 times mod of xi minus yi into mod of xj minus yj for I not equal to j, for I not equal to or I less than j, and therefore this inequality hold, and this is nothing but d1 of x bar y bar its square. This implies d1 of x bar, d2 of x bar y bar is less equal d1 of x bar y bar. Say 1. Okay. Now In this sum, mod of xi minus y. Now, mod of xj minus yj is less equal. Okay. Or if I take its square here, it is less equal. It is less equal summation of xi minus yi square I equal to 1 to n for every j is equal to 1 to up to n. And therefore, mod xj minus yj is less equal d2 of x bar y bar for every j is equal to 1 to up to n. Right? So from this, I will get, therefore summation of j is equal to 1 to n mod xj minus yj is less equal d2 of x bar y bar. Sorry, n times. If I take the square root here, square root, okay, each term, so I will get this is less equal n times by taking square root. So square root is less equal square root here. So if I take n times sum, so it is n times d2 of this, and therefore d1 of x bar y bar is less equal n times d2 of x bar y bar. From 1 and 2, from 1 and 2, we get d2 of x bar y bar is less equal d1 of x bar y bar is less equal n times d2 of x bar y bar for any x bar y bar belongs to Rn, and k1 is equal to 1, k2 is equal to n greater than 0. Therefore, d1, d2 are equivalent matrix. Right? Now we have to show that d1, d infinity are equivalent. Okay. Second, to show d1, d infinity are equivalent. So for this, d infinity of x bar y bar is equal to maximum of mod of xi minus yi, 1 less equal I less equal n. This must be less equal summation of mod of xi minus yi, I equal to 1 to n. Because among these sum of n terms, this maximum is one among them, and this sum contain more additionally non-negative terms, and that's why this will get, this is to be d1 of x bar y bar. This is now 3. Okay. Now mod of xj minus yj is less equal summation of mod of xj minus yj. What I have to show? Summation is less equal maximum of modulus of xi minus yi, 1 less equal I less equal n for every j equal to 1 to up to n. Is it right? So if I take summation summation j is equal to 1 to n mod xj minus yj is less equal n times. This is nothing but d infinity of x bar y bar. And but this is nothing but d1 of x bar y bar is less equal n times d infinity of x bar y bar. From 3 and 4, from 3 and 4, we get d infinity of x bar y bar less equal d1 of x bar y bar is less equal n times d infinity of x bar y bar for any x bar y bar belongs to Rn, and k1 k2 k1 is equal to 1, k2 is equal to n greater than 0, and therefore d1 d infinity are equivalent matrix on Rn. Now we have to show that we have proved d1 d2 d infinity. Now d2 d infinity. Okay. Third, to show d2 d infinity are equivalent matrix. D infinity of x bar y bar its square is equal to maximum of mod of xi minus yi 1 less equal I less equal n. Its square must be less equal summation of xi minus yi square I equal to 1 to n, that is d2 of x bar y bar, which implies d infinity of x bar y bar is less equal d2 of x bar y bar. This is 5. Right. Now, if I take mod of xi minus yi, xj minus yj, its square is less equal summation of I equal to 1 to n xi minus yi its square for every j is equal to 1 to up to n. Right. So therefore mod of xj minus yj is less equal, if I take square root of this will become d2 of x bar y bar, taking square root. And if I take sum of this, if I take maximum of this, for every j, this is true. Sorry, I am doing same thing here. So we are not interested in that. Okay. Oh, sorry. Now mod of xj minus yj is less equal d infinity of x bar y bar is equal to maximum of mod xi minus yi 1 less equal I less equal n, and therefore xj minus yj its square is less equal d infinity of x bar y bar its square, and therefore summation of xj minus yj its square j is equal to 1 to n. This must be less equal n times d infinity of x bar y bar its square, taking square root. we will get d2 of x bar y bar is less equal to root n into d infinity of x bar y bar. This is 6. So from 5 and 6, from 5 and 6, what we are getting? D infinity of x bar y bar is less equal d2 of x bar y bar is less equal to root n times d infinity of x bar y bar for any x bar y bar belongs to Rn, and k1 is equal to 1, k2 is equal to root n greater than 0. Therefore, d2 and d infinity are equivalent matrix on Rn. Thus we proved any two matrices among define these three matrices are equivalent matrix for Rn. And for this, we have used sufficient condition for equivalent matrix. Okay. So we'll take one more example of equivalent matrix. Let XD be matrix space, any matrix space, and D1, D2 are matrix defined for XR, defined for XR. D1 of XY is equal to d of xy upon, we have proved this, 1 plus d of xy, d2 of xy is equal to minimum of 1 dxy. So that d1, d2 are equivalent matrix. Equivalent matrix for X. So by writing solution, write the matrix also, write matrix also, because that is useful. So here for any xy belongs to X, d of xy upon 1 plus d of xy is less equal 1 and d of xy. Since 1 upon 1 plus d of xy belongs to 0, 1. Belongs to 0, 1. This implies d1 of xy is less equal d2 of xy. d2 of xy 1. Okay. Now d2 of xy, okay, for d2 of xy less equal 1, d2 of xy less equal 1, d2 of xy is equal to minimum or less than 1 minimum of 1 d of xy, this is equal to d of xy, and this must be less equal 2 times dxy upon 1 plus d of xy. In bracket, since dxy into 1 plus d of xy is less equal to dxy, for dxy less equal 1. Again, for d2 of xy greater than 1, sorry, d of xy sorry, here for d of xy less equal 1, d2 of minimum is nothing but d of xy. For d of xy greater than 1, d2 of xy is minimum 1 dxy, this is equal to 1, and this must be less equal 2 times dxy upon 1 plus d of xy, since which is equal to 2 d1 xy, since 1 plus dxy is less equal to dxy as d of xy greater than 1. Okay, thus what we proved, d2 of xy is less equal 2 times d1 of xy for any xy belongs to x. This is 2. From 1 and 2, from 1 and 2, we get d1 of xy is less equal d2 of xy is less equal 2 times d1 of xy for any xy belongs to x, and k1 is equal to 1, k2 is equal to 2 greater than 0. Therefore, d1, d2 are equivalent matrix for xd for x. So, in this lecture, we have used sufficient condition to show that two matrices defined on set are equivalent. So, take one exercise. So, we'll take exercise to be let di I equal to 1 to n be matrix for set x. We'll define two matrices. For that, d star of xy is equal to maximum of di xy 1 less equal I less equal n xy belongs to x, and d double star of xy is equal to summation of di xy, I is equal to 1 to n, xy belongs to x. So that first d star, d double star are matrix for x, and second d star and d double star are equivalent matrix. So if I have n number of matrix defined for set x, and if I define d star by using maximum of di x y and d double star is sum of di x y, then that both function defines matrix for x and they are equivalent. So this is the exercise for you, for your practice. Prove that d double star are matrix. It is too simple. By using properties of matrix of di's, you can easily show that are matrix. So for both, whatever done for this summation of di xi xy, this is just like as taxi cab matrix for Rn. Okay, d2, d1 of x bar y bar is equal to summation of mod of xi minus y. It is just like as this. And this is just like as d infinity. This is just like as d infinity. D infinity of x bar y bar is maximum of mod of xi minus y. So on same line, you have to prove that these two functions are matrix and try to show these are equivalent matrix. So how we proved that d1 and d infinity for Rn are equivalent matrix? On same line you have to prove these two matrices are equivalent. With this discussion, we will stop our session here. Thanks. Bye-bye. Visit, listen our lectures very carefully. If you have any difficulty, you can ask me through comments, and please like the lectures, subscribe channel, so it will be helpful for me. Thanks.